The learning objectives for this video are to discuss enantiomers in the tetrahedral carbon, chirality, optical activity, Pasteur's discovery of enantiomers, and rules for specifying configuration of chiral centers. We've been talking about isomers in this class, and so far we've talked about two types: constitutional isomers, which have the same molecular formula but a different connectivity of atoms; stereoisomers, which have the same molecular formula and constitution but a different spatial arrangement of atoms. Of the stereoisomers, there are two kinds. There are conformational or conformers. Those are the ones that we depicted with the Newman projections. Those rapidly interconvert at room temperature because they just have to rotate around a bond to interconvert. Therefore, you cannot separate those. Then the other type are configurational isomers, which are stereoisomers that cannot interconvert unless covalent bonds are broken. And these can be separated. And the two types of configurational isomers are cis-trans isomers, which we've discussed, and isomers that contain asymmetric centers. That's the new type of isomer I'm discussing in this video. So recall, with cis-trans isomers, if you have a ring such as cyclohexane with two groups on it, if they're both on the same side of the ring, as in this example they're both on the top face, that would be the cis isomer, versus if one methyl is up and one methyl is down, that would be the trans isomer. The other type of stereoisomer, that's a configurational stereoisomer, has a chiral center. So what do I mean by chiral? A chiral object is asymmetric, which means it is not the same as its mirror image. And you can test whether two objects are identical by seeing if they are superimposable. The classic example of this are your right and left hands. They are mirror images, but you can't superimpose them one on top of the other. The thumbs won't line up. So chiral molecules do not have a plane of symmetry and are not superimposable on their mirror image. Achiral molecules do have a plane of symmetry. If we look at these two molecules, here if we cut this molecule right down the center, we can see that the hydrogens on the left and the right mirror each other, so there is a plane of symmetry. However, if I cut this molecule right down the center, then we have a hydrogen on one side and an OH on the other, so there is not symmetry in that molecule. If we think about everyday objects like a coffee cup, you can see that if you split this coffee cup right down the center, the right half looks just like the left half, so that does have symmetry. But if we look at a hand, so if you cut your hand right down the center, the left half with your thumb does not look just like the right half. So the hand would be chiral, but the coffee cup would be achiral. Frequently, chirality results when a carbon atom is bonded to four unique groups of atoms. So for example, if these different colored balls represent different groups, and this is a carbon in the center, that carbon is connected to four different things. And while it has a mirror image, it is not superimposable on that mirror image. And you can make a model and prove this to yourself. So if we have an actual example, so here Me means methyl, Et equals ethyl. This carbon is bonded to four different groups: a hydrogen, a methyl, an ethyl, and an OH group. So it does have a mirror image. If we imagine the mirror right here, this would be its mirror image. But if you make this model with your model kit, try to superimpose them on each other and you will find that you cannot. And that's because it's chiral. There's no plane of symmetry. So a chirality center is a point in a molecule where four different groups are attached to carbon. And this is the cause of chirality. So for example, if we look at 5-bromodecane, this carbon right here is chiral. Notice the groups attached to it. You've got a hydrogen here and a bromine. And then over here you've got a butyl chain, so a 4-carbon chain. And then on the left you have a 5-carbon chain. So those are four different groups on that carbon, making it a chiral center. You will often see other names used instead of chiral center, such as stereocenter, stereogenic center, or asymmetric center. These terms are all interchangeable. Now let's look at these three examples. Each highlighted carbon is bonded to 4 different groups and is a chirality center. Now, first of all, with bond line structures, when it's not in a ring, we draw them in a zigzag format. And we can indicate spatial arrangement by using solid and hatched wedges. So we could draw the chlorine like this as shown. Now the hydrogen isn't depicted because we don't draw in hydrogens bonded to carbons, but we could add that in, and that would have to be on a hatched wedge, because when we're using the zigzag format for tetrahedral carbons, every carbon will have 2 bonds in the plane and 2 bonds out of the plane, like this. Sometimes we depict things like this, sometimes we don't. But when we have chiral centers, we will use the solid and hatched wedges. Just like when we saw the cis-trans isomers, we had to have a solid or hatched wedge to understand if it was up or down. With chiral centers, we definitely need to have that information that's conveyed with the solid and the hatched wedges. So if I look at this molecule, and I'm looking at that chiral carbon here, so let's look at the 2 groups in the plane. We've got a methyl here, and we've got an ethyl on the right, and then we have a chlorine and a hydrogen. So that's 4 different groups. And then I can do that same analysis. So I'm going to draw in my hydrogen because it's going to help me do this analysis. So if I look at this carbon, it's got an OH group, a hydrogen, and on this side it's got an ethyl, and on this side it's got a propyl. Then if I look at this carbon, notice it's in a ring, but we're still going to do the same type of analysis. We've got a bromine atom and a hydrogen. And then go around the ring on each side and see if you see a difference. So when I go to this, to the right, I see a carbon that's double bonded to another carbon. And then when I go to the left, I see a carbon that's singly bonded to another carbon. So the right and the left diverge. So that carbon here is bonded to 4 different groups. So pause the video and see if you can figure out how many chirality centers are in each of the following compounds. It may help you to draw in your hydrogens. So in this first compound, and it's drawn in a chair conformer, it has no chirality centers because this carbon has an H and an OH. Well, those are different, but when you go around the ring, you get no point of divergence. There's also a plane of symmetry going through that molecule. Now if we go over to this cyclohexane, and I can draw in my hydrogens if I want, I see that this carbon does have 4 different groups attached. It has the OH group, the hydrogen, and then when I go around the ring, when I go this direction I see a CH2, and then when I go this direction I see a CH attached to an OH. So those are different. So that's definitely a chiral center. And sometimes we indicate chiral centers with an asterisk. Then if I do the same analysis with this carbon, I also see it's chiral. Now let's look at the bottom 2 groups. So first of all, a carbon with 3 H's or 2 H's is not chiral because it doesn't have 4 different groups. So this has 3 H's, so that can't be chiral. This has 3 H's, so that can't be chiral. This has 2 H's. I'm going to put in my H here. I'm going to put in my H here with the appropriate wedge, and I'm going to put in my H here. So this carbon, you might at first think it's chiral, but it's not. It's got a methyl group here and a methyl group here. So it has 2 methyl groups, so it's not chiral. Now if we go to the next carbon, this carbon has a hydrogen, a CH3 group, and then it has an isopropyl group on this side and an isobutyl group on that side. So that is chiral. Now let me look at the next carbon. So this carbon has a methyl, a hydrogen, an ethyl, and then this entire piece of the molecule, which is not a methyl, an ethyl, or a hydrogen, so that also is a chiral carbon. And then finally, with this, if I add in my hydrogens, I can see that this carbon has a methyl group, an ethyl group, a hydrogen, and the rest of the molecule. So that has 4 different groups. And then this carbon has a hydrogen, a methyl, this double bond containing fragment, and then this sec-butyl fragment. So that also is a chiral carbon. We have a special word for molecules that are mirror images of each other but not superimposable upon each other, and that is enantiomers. So if we look at this molecule, that is a chiral carbon. It has 4 different groups, and then these 2 mirror images would be non-superimposable mirror images or enantiomers. Both of these compounds are superimposable on their mirror images, so we would not call those enantiomers. So if we wanted to draw a mirror image of a compound, imagine that there's a mirror right here, and I could draw in my hydrogen that's not shown. So to draw that mirror image, would look like this. And this is indeed a chiral compound, and that's the chiral carbon. It has a chlorine, an ethyl, a methyl, and a hydrogen. And if you were to make the model of this compound, you would find that you cannot superimpose it upon its mirror image. An often easier way to draw the enantiomer of a chiral compound is to just invert the dashes and wedges of a chirality center. So if we had this, instead of imagining a mirror and drawing the reflection, we could just put the chlorine atom on the dashed bond, the hatched bond, and draw this. The same thing with this molecule. Instead of having the methyl group on the solid wedge, I would have it on the dashed wedge. And notice, however, here, we can draw this stereochemistry, but this compound is not chiral. If you look at this carbon, it has 2 methyl groups attached. So inverting the dashes and wedges actually provides an identical structure. Chiral compounds possess optical activity. In this, light passes through a polarizer. Polarized light is rotated in solutions of optically active compounds, and that's measured with an instrument called a polarimeter. Levorotatory are optically active substances that rotate the plane of polarized light in a counterclockwise direction. Dextrorotatory refers to optically active substances that rotate the plane of polarization of plane polarized light in a clockwise direction. A polarimeter is the instrument used to measure this rotation of plane polarized light. And then the angle between the entrance and the exit plane is the optical rotation. This figure shows a representation of a polarimeter. You have a light source which is emitting unpolarized light. It then passes through a polarizer, so now the light is all going in one direction. And then it hits the sample tube, which contains chiral molecules, and that light, the plane of that polarized light, is rotated to a certain degree depending upon the substance. And then in the analyzer, you can measure that degree of rotation. The specific rotation for a chiral compound can be measured under standard conditions using this formula. So observed rotation in degrees is on the top, and then you divide that by the path length in decimeters times the concentration of the sample in grams per cubic centimeters. Here are some examples of specific rotations for various organic molecules. So for penicillin, plus 233, for camphor, plus 44.26, but notice chloroform, it's 0. That's because chloroform is not chiral, it's not optically active. The same with acetic acid. So here's an example. Suppose you had a 1.5 gram sample and you dissolve it in 10 milliliters of ethanol and place it in a sample cell with a 5 centimeter path length. The observed rotation of the sodium D line was 1.21 degrees. Calculate the specific rotation for this compound. So what's given is the path length at 5 centimeters. You want to first convert that to decimeters. And then the rotation is 1.21 degrees. And then the concentration, we want to convert to grams per milliliter to get to that number. So using that number, you get to a specific rotation value of plus 16.1 degrees. Louis Pasteur discovered enantiomers when he was working with sodium ammonium salts of tartaric acid, and he found that they actually crystallized into right-handed and left-handed forms, and equal concentrations of these forms had opposite optical rotations. This is a representation of those crystals from Pasteur's original sketches, and this is what sodium ammonium tartrate looks like. The final topic is to specify configuration at a chiral center using the Kahn-Ingold-Prelog rules. The first rule is that you want to look at the 4 atoms directly attached to the chiral center and rank them according to atomic number. The atom with the highest atomic number has the highest ranking, and the atom with the lowest atomic number has the lowest ranking. So for example, bromine would have a higher ranking than chlorine, and so forth. And deuterium, which is an isotope of hydrogen, would have a higher ranking than the more abundant hydrogen isotope. The second rule is that if a decision cannot be reached by ranking the first atoms in the substituent, you then look at the second, third, or fourth atoms until the difference is found. Rule number 3 says that when you're looking at multiple bonded atoms, you consider that equivalent to the same number of single bonded atoms. So for example, if we're looking at this carbon, we think of it as being bonded to HOO, and if we're looking at this oxygen, we think of it as being bonded to 2 carbons. The R configuration is the configuration of the chirality center if the curved arrow is drawn clockwise. The S is the chirality center configuration if the curved arrow is drawn counterclockwise. And the absolute configuration is the exact 3D structure of the chiral molecule. So what do I mean by the clockwise, counterclockwise? If you have your chiral carbon and you've assigned priorities to all of the groups, so 1, 2, 3, and 4, where 1 would be the highest priority, so the group with the highest atomic number, and then 4 would be the lowest priority. You want to reorient the lowest priority group away from you so that it looks like a steering wheel. And then you're going to draw an arrow from 1 to 2 to 3. And if when you draw that arrow, the arrow is going in a clockwise direction, we call that the R configuration. If, on the other hand, it's going in a counterclockwise direction, that's called the S configuration. Handheld models are very helpful in arranging the molecule in space so that the lowest priority group faces away from you. If you're drawing it on paper, there's some other tricks that you can use. So you would want your lower priority group 4 to be on the dashed wedge back. So here, if I draw my arrows 1 to 2 to 3, I see that that is going in the counterclockwise direction, which is going to give us the S configuration. Now, if I switch the 2 groups, 1 and 4, I will get the opposite configuration, the R configuration. Knowing that by switching 2 groups, you get the opposite configuration, you can redraw the molecule on paper to get the lowest priority group back. So for example, if I have this molecule, and in order to figure out R and S, I need the lowest priority group, group 4, on the dashed wedge back. So if I switch 3 and 4, then I would get to this molecule. Now I've switched 2 groups, so I will have the opposite configuration. So if I draw my circle now, 1 to 2 to 3, that looks like the S configuration. But the original molecule must have been the R configuration since I changed 2 groups. Now, if I wanted, I could make the first change and then make a second change, keeping the lowest priority group back. And by doing that, I would get 1 to 2 to 3, the R configuration, which matches that of the originally depicted molecule. So switching two of the groups twice returns the original configuration, but allows us to put the 4 priority group pointing away. So there's a couple ways. The first thing is you need that lowest priority group on the dashed bond pointing back. If you switch two groups to do that, whatever configuration you get will be the opposite of what it is. However, if you make another switch, a second switch, then the configuration you get will be the same as the original depiction. Personally, I will just switch it once and know that my answer is the opposite of what I'm getting, rather than doing two switches, but either way works. Here's a summary of how to assign configuration of a chiral center. First, you identify the 4 atoms directly attached to the center. 2, you assign a priority to each atom based on its atomic number. The highest atomic number receives priority 1, and the lowest one receives priority 4. 3, if 2 atoms have the same atomic number, you move away from the chiral center looking for the first point of difference. And when doing this, remember that a double bond is treated as separate single bonds. 4, you rotate the molecule so that the lowest priority group is on the dash, going behind the plane of the page. And then 5, you draw your arrow 1 to 2 to 3 and figure out if it follows a clockwise R or counterclockwise S orientation. So try this example. Can you assign the R or S configuration? The first thing I would do is draw in my hatched bond with my hydrogen. Now I'm going to look at this carbon, that's my chiral carbon, and I'm going to go 1 atom out. So the hydrogen will be the lowest priority group, that will be 4. Then I have nitrogen versus carbon versus carbon. Nitrogen is a higher atomic number than carbon, so that's going to be my highest priority group. Now to differentiate between the 2 carbons, I have to look at what they're bonded to. So this carbon's bonded to a hydrogen, and another carbon. This carbon here is bonded to, we can think of it as being bonded to 3 oxygens. Since it's double bonded to oxygen, we count that twice, and then it's also singly bonded to oxygen. So oxygens have higher atomic numbers than all 3 of these atoms, so this will be the next highest priority, followed by this. Now I'm going to draw a curve connecting the groups 1 to 2 to 3. 1 to 2 to 3. And now I'm going in the clockwise direction, so this would be the R configuration.